But yeah.
Do you happen to know, like, was this always an auditorium?
Library.
As long as, like, that's been the place stats? Or?
Well, see, I think it was originally the library, but it has been auditorium for a long time.
Interesting. Cool.
Yes, it's not optimally built for being an auditorium.
Okay, and so the part of the 2 stories was because it was the library space? Or?
I mean, I don't actually know things,
Yeah.
but that's what I've been told.
Oh, interesting. Yeah. Super cool. All right. Yeah, at least till 11.
Do you usually start a little late here?
Like a minute or 2.
Oh, okay. Not the whole 5 minutes that
Yeah.
they do at MIT.
Yeah, exactly. Halfway in between. Right. You're not teaching this semester, are
I
you?
am.
Or you
yeah.
are? Okay.
Freshman in cost mechanics.
Amazing.
It's
That's
fun.
really cool.
It's
That's
fun.
really cool. Is it like in a big auditorium?
So yeah, I'm doing recitations for it actually.
Okay.
But so.
Okay.
But
So it's like smaller groups at a
Yeah,
time?
yeah.
Okay, I see.
Mhm.
And then is it like the lectures are video or?
No, the lectures. So at MIT, like the lectures and recitations are both taught by professors, but like different ones. So there's one
so it's
professor
like
who's doing the lectures, and then
Oh, super interesting.
yeah,
Ah, cool.
it's a good way to sort of ease into it.
Well, and
But,
for the
yeah.
students, they actually are getting to interact with the faculty, so
Yeah.
that's a
Yeah.
good thing.
Yeah.
Um,
definitely.
yeah. I think I'm on your schedule for later. And I have a times question for you.
Okay. Yeah. Looking forward to chatting.
Yeah, sounds great.
Yeah.
It's the sort of like spooky entrance.
Today we are very happy to have Sarah Millholland from MIT. Sarah got her PhD from Yale University in 2020, and after that she is a NASA Second Fellow in Princeton, and now she's starting as assistant professor at MIT. Today she is going to, she is an expert in various aspects of exoplanets, and today she will talk about the regularity and the anomalies for short period planets. I will let Sarah take it away.
Great. Thank you for the introduction. I'm really happy to be here today. As you just said, I just moved to MIT in September, so I'm really excited to be kind of joining the Cambridge astronomy community. So today I'm going to talk about some of the stuff our group is working on, which is, broadly speaking, motivated by the goal of understanding the demographics and the diversity of exoplanetary systems. And so in this talk, I'm going to focus on the ubiquitous class of short period exoplanets, and I'll highlight a number of interesting regularities and anomalies that we see within the arrangements of these planetary systems. And I'll talk a bit about how we can understand and explain these regularities and anomalies using a combination of observational characterization and orbital dynamics theory. So I think that still one of the most remarkable discoveries in the field of exoplanets thus far is just this realization that roughly half of Sun-like stars are accompanied by very close-in small planets with orbital periods ranging from days to months. So these are planets that we don't have represented in our own solar system. And I'm really interested in this population, both because they kind of represent the dominant fraction of planets that we've discovered to date, but also these planets enable some very precise orbital and physical characterization. So this is a slightly different view of looking at this population of short-period planets. This is a graphical representation of planets discovered by the Kepler mission, where the radial coordinate is the logarithmic semi-major axis. And so again, we can see that this population of planets contrasts very sharply with our own solar system, whose inner edge is marked by Mercury's 88-day orbital period. These planets tend to be a little bit larger than the Earth. They're most commonly between the sizes of Earth and Neptune, as represented by the sizes of these dots. And then lastly, a relatively large fraction of these planets are found in systems that have more than one transiting planet, as shown with the sort of fraction at the top. And it's these kind of systems that have more than one transiting planet that I'm primarily going to focus on today. So these systems that have multiple transiting planets exhibit a lot of very interesting sort of structure and regularity. The first of these that the Kepler mission discovered was the Kepler-11 system, which has at least 6 planets. So this system is very compact. The orbits are very nearly circular, very nearly coplanar. And so all of these planets are orbiting inside the orbital radius of Venus, with at least a few of them having fairly regular orbital spacing. So this system exhibits a lot of structure in the sense that it's kind of a low degree of complexity. It's kind of almost as architecturally simple as we can imagine planetary systems getting. And if we look at these same features on the scale of the whole multi-planet population discovered by Kepler, we can see that this orbital structure continues. So the systems as a whole tend to have fairly low eccentricities and inclinations on average. This is kind of represented by these distributions on the left, which roughly show the current observational constraints on these. So this means that their orbits are, again, very nearly circular, very nearly coplanar. In addition, the distribution of orbital spacings between these planets peaks fairly sharply at around a characteristic spacing of about 20 mutual Hill radii. So the mutual Hill radius is a kind of a characteristic length scale for dynamical interactions between planets. And so planets need to be spaced by more than about 5 to 10 mutual Hill radii to be dynamically stable. So this characteristic spacing of around 20 mutual Hill radii indicates that these planets are kind of dynamically packed, piled up near their stability limit, and but have this kind of typical sort of spacing. So this is, again, sort of pointing to this preponderance of these very nicely spaced, not super complex multiple planet systems. Fascinatingly, this structure actually continues beyond the orbital characteristics and into the physical properties of these planets. And that is that planets in the same system tend to have similar masses and radii. This sort kind of intra-system uniformity was first pointed out by Weiss et al. And also in our work from 2017. So this is fairly easy to see for the radii on the right. If you kind of scan your eyes down through these various different multi-planet systems discovered by Kepler, you can see that the sizes of the planets are more similar to their neighbors than you would expect if these planetary systems had been just assembled from planets pulled randomly across this population. And this depiction also makes it fairly easy to see this fairly kind of uniform orbital spacing between planets. On the left here, we can see this intra-system uniformity for both masses and radii, where all planets in the same system have the same color and are connected by lines. And so if we measure the dispersion of planetary systems on this mass-radius plane for these observed systems, we can see that they're a lot less dispersed than you would expect if the population was just assembled from planets pulled across the population. So this is actually easier to see if I kind of toggle back and forth between these real systems and a random permutation in which the sort of mass and radius pairs are shuffled. So this very fascinating tendency for these planets to have very regular orbital spacing, very nearly uniform radii and masses, is known collectively as the peas in a pod patterns, kind of just due to this visual similarity between these planetary systems and a collection of peas in a pod. So if you're interested in learning more about this and more about some reasons for why we think this might exist theoretically, I'd encourage you to check out this recent Protostars and Planets review that we tried to explore kind of the ideas for why this might be showing up in the data. This chapter just appeared on arXiv fairly recently. But so, okay, I've kind of just shown now that these systems have a lot of structure in both their orbits and in their physical properties. So it kind of seems like everything's very straightforward. We can understand these systems very well. But that's not kind of the full story. So the complete story isn't that simple. And if we kind of take a closer look, we can contrast a lot of this sort of first-order structure that we see with some kind of second-order architectural anomalies. So with the word architecture, I'm referring to sort of the arrangements of planetary orbits and physical properties within a given system. And by anomalies, I mean kind of complex deviations from this first-order structure. So there are actually lots of examples of this, but just to give you sort of a flavor of these, I want to point out a few examples here. So one example is that if we look at the orbital period ratios of pairs of planets from the same planetary system, we can see that this distribution of period ratios is fairly smooth overall, but there are kind of slight overabundances just wide of the 3:2 and the 2:1 period ratios. These locations are special. They're called the first-order mean motion resonances. Another example is that we see these planetary systems with this very tightly packed, nicely spaced architectures, but the systems kind of appear to just end at some point, even though perhaps there might have been further planets outside. I'm going to talk a lot more about this today, but this is sort of a potential example of an architectural anomaly. And finally, another example is that there are a subset of systems that appear to have sort of an extremely close-in outlier planet that appears to be sort of pulled off from the innermost edge of a otherwise fairly typically spaced multi-planet system. So these are all kind of examples of these architectural anomalies that I've worked on in the past, but I'm going to talk in detail about one of these today. But all of these architectural anomalies require some explanations, and if we can figure these out, we can better understand the planet formation and evolution processes that lead to these interesting anomalies in the data. So it turns out that a lot of these architectural anomalies likely are arising from some form of dynamical sculpting. So that is evolution of the system largely after its initial formation in the protoplanetary disk. And these dynamical effects can include things like resonance interactions between planets, tidal interactions between the planets and their host stars because they're so close in, irradiation-driven effects from the host star, or planet-planet collisions, giant impacts, and so on. And so in my work, I largely kind of study the role that these dynamical processes have in explaining some of the patterns that we see in the observations. So in the remainder of this talk, I'm going to focus on these architectural anomalies and discuss two specific examples. So broadly speaking, the two anomalies I'm going to discuss are related to these two questions. First, what sculpts the outer edges of planetary systems? And then second, what sculpts misalignments between planetary orbits and their host stars? And so I'll talk about these kind of using this combination of data and orbital dynamics. Okay, so the first architectural anomaly I want to discuss pertains to the outer edges of these planetary systems. So just to kind of review what we've talked about so far, these systems have this very nearly circular coplanar orbits, this regular orbital spacing, nearly uniform radii and masses, such that we often say that they kind of resemble peas in a pod. However, there is an important feature of these systems that hasn't really been discussed much before, and that's kind of what sets the edges of these pods, or the locations of the innermost and outermost planets in these systems. It's important to note that the planets that we see are just the observed planets, and there may be further out planets that we haven't yet detected. So an interesting question, though, is how far out does this underlying system of compact planets actually go? We know that it can't just kind of go out indefinitely far. So can these outer edges of the observed systems tell us anything about the outer edges of the underlying system of planets? So I first kind of want to provide some kind of heuristic motivation for why there appears to be something interesting here. And so to do that, I'm going to sort of take a preliminary look at a set of these compact multi-planet systems that have 4 or more planets that were discovered by the Kepler Prime mission. So this is actually a random subset of about 75% of that total sample of multis from Kepler, just to be able to kind of see these on this slide clearly. So Kepler required that planets have to transit their host star at least 3 times in order to detect them. And this kind of combined with the mission's approximately 4-year observational baseline indicates that the maximum detectable period is roughly around 500 days. So this 500-day threshold is marked here, and we can see that in all of these systems there is a fair amount of space between the outermost detected planet in each system and this maximum detectable orbital period, such that in all of these systems, planets at these intermediate periods could potentially have been detected, but were not. Of course, it gets harder to detect planets at longer periods, so perhaps this isn't really surprising at all, but it's definitely something worth looking into further. So to further extend this heuristic argument, let's consider adding kind of an additional hypothetical outer transiting planet in each one of these systems, with each of these hypothetical planets' periods and radii dictated by what we would expect if the system just continued in its peas in a pod architecture. Now, though, let's consider in each system the minimum planetary radius that would have been detected according to some just nominal detectability threshold. That's indicated with the yellow dots overlaid on top of these purple dots. So remarkably here, in every single case, the purple dots are larger than the yellow dots. So the ratio between them is indicated with the values on the right-hand side, and they're all larger than 1. Meaning that all of these hypothetical planets would nominally have been detectable if they were there. So this heuristic kind of argument or experiment has demonstrated that if there were additional transiting planets in these systems, and if they had properties kind of in line with our expectations based on the peas in a pod patterns, then we would generally expect these to be detectable. But this appears to be inconsistent with the lack of detections beyond the observed planets. So with this heuristic idea in mind, we kind of set out to explore this in a more robust way. So the key question that we were interested in is, if these Kepler multi-planet systems hosted additional outer planets that had similar properties as these known planets, how many of these would we expect to be both transiting and detectable? To address this question properly, there are two kind of things you need to account for. One is just the geometric transit probability, or the likelihood that if we add an additional planet to the system, that this would also be transiting the host star. And this depends on the mutual orbital inclinations between that additional planet and the others in the system. The second is the detection probability, or the likelihood that this additional planet, if it was transiting, that it would have a transit signal large enough to be detected. And this relates to the planet's radius and its period, as well as the sort of noise properties of the host star. So skipping kind of the details of how we actually calculate these geometric transit probabilities and detection probabilities, we performed sort of a detailed exploration of the detectability of hypothetical planets orbiting beyond the outermost detected planets in these sets of multi-planet systems. So we started with 64 Kepler systems that had 4 or more known planets, and we added just one additional hypothetical planet in each one of these systems, and kind of with its properties dictated by our expectations based on the P's in a pod patterns. And then we calculated the expected number of these that we would expect to be both transiting and detectable. So here's the result of these calculations, where this distribution is showing the expected number of these hypothetical planets that would have been both transiting and detectable. So we can see that across these 64 systems, the hypothetical planets should have been detected in roughly about 15 to 30 of them or so, which is a lot more than the sort of 0 detections of additional planets in the actual observed systems. It's important to note that this distribution has to be positive by definition, so it's a little bit more meaningful to compare this to analogous results that we got using simulated planetary systems, which we found were kind of like piled up very near 0, consistent with 0 to within 2 sigma or so. So the key kind of takeaway here is that we're finding that these additional planet detections would have been expected in more than about 35% of these systems, which is inconsistent with the lack of the observed detections at around the 7 sigma level. Crucially, though, this is actually a lower limit on the extent of this discrepancy, because we would have expected even more detections of hypothetical planets if we assigned more than just one of them per system. So we're finding here that it doesn't appear that the outer edges of these systems can be explained by considerations of just geometric and detection biases alone. So these results indicate that something in the underlying planetary systems is sort of breaking down at the outer edges. And we can kind of review the possibilities here. One option is that there is an average truncation, or a decrease in the occurrence of planets at longer periods. A second possibility is that perhaps the orbital spacings get larger at larger orbital periods. A third possibility is that perhaps the planetary radii get smaller and thus harder to detect at longer periods. And a final possibility is that perhaps the mutual inclinations between orbits grow at longer periods. So to summarize, we're finding evidence either for some form of outer architecture truncation or some kind of breakdown of these P's in a pod patterns at longer periods. The natural kind of question now then is, what's causing this truncation or this change in these outer architectures. So if this is correct, this is really a significant new mystery about the nature of these systems, and it has to be kind of tied to some physical or dynamical explanations. So based on the literature that I reviewed for this, I don't think that there's necessarily one kind of surefire answer here, but there are some existing planet formation theories that do predict a truncation or change in the architectures right around 0.5 to 1 AU. So I want to briefly kind of comment on one that I found particularly compelling. Okay, so first, it's key to note that there's still not widespread agreement on how these systems even form. There's kind of two major schools of thought. First, that they form in situ, or that they form at larger distances, perhaps around an AU, and then migrate closer to the star through disk-driven migration. In the migration model, the migration is usually dominated by the negative Lindblad torque, and it's directed inwards towards the star. But there are some regions where the positive co-rotation torque is dominant, and the migration is directed outwards. So these heat maps are showing the net torque in this kind of semi-major axis and planet mass space over time, according to this recent paper by Zawadzki et al. And so the blue regions are corresponding to regions of inward migration, the red to regions of outward migration. So we can see that there's this kind of time-evolving region that acts as a sort of migration trap that prevents inward migration of some planets. And so as a result of this migration process, the planets that are massive enough to avoid this trap can migrate into the inner edge of the disk, and leaving kind of smaller planets outside with a bit of a gap in between. And so Zawadzki et al. Showed that when they look at this across kind of a population level, they find that this migration framework would naturally produce kind of planetary systems that tend to be bifurcated into two groups, those with sort of shorter periods and longer periods, with an underabundance right around 100 days orbital periods or so, which would be sort of precisely consistent with our observational finding of a kind of fall off or at that orbital separation. Yeah?
Is a simple way of thinking about it like segregation as a result of gravity, that the star is bringing in the heavier things, just like dust settles in air, you know?
Yeah, it's pretty similar to that. I think that the massive planets migrate faster and are also able to avoid this trap, so they settle in close to the star. The smaller things migrate slower and also get trapped by that. And yeah, so it's like this separation effect that happens like that. Yeah. So I think this is a pretty compelling possibility for this. It's definitely not a kind of unique explanation for these results, though. So there are several other theoretical possibilities for what might be causing this truncation or this change in the outer architectures. And so in particular, one idea that I'm exploring with an undergraduate student, Nicole Sobsky, is that perhaps these inner systems are limited in their extent due to perturbations from exterior giant planets. So observations from the last few years have shown that whenever a planetary system contains close-in super-Earths, that it appears to be more likely to also contain a distant kind of Jovian analog planet as a significant kind of enhancement relative to just the occurrence rates of giant planets around field stars that don't have inner super-Earths. So it's like the conditional probability is higher. So these distant planets are found at around a few AU. Their orbits are often fairly eccentric and potentially inclined with respect to the inner system. And so it's possible that these distant giants kind of create a sort of zone of instability that would sort of limit both the formation and the long-term stability of any planets that try to form in this kind of intermediate zone. So we're still kind of in the process of exploring this idea. But whatever the cause is of this sort of apparent edge or truncation, we hope that our work will kind of offer clues for how these close-in systems form.
This sounds like an explanation for the asteroid belt in the solar system, except that it's much further out, right? It's not at the 100-day. So why would there be this difference?
Yeah, that's a good question. So one thing is that Jupiter and Saturn are fairly circular, have fairly circular orbits, and that they're coplanar with the rest of the solar system. But these guys are often pretty eccentric, and they can have orbital tilts, and when both of those things happen, they can create sort of stronger interactions from a distance, just due to kind of eccentricity excitation of the inner region. Yeah, that's a good question.
So is there any correlation with where you find the last planet is and the snow line? Like, is it a constant ratio?
That's a good question. We haven't looked at all of how sort of, if I go back to...
Because those stars vary a lot in mass and
Yeah.
luminosity, I assume. So
Yeah, we haven't looked at all like whether there's any correlations in like where this outer planet appears with stellar properties.
yeah,
But that would be an interesting thing to look at.
yeah, just insolation.
Yeah, like sort this, I guess, by stellar mass or insolation and see. That's a good idea. Okay, so in the last kind of like 5 to 10 minutes or so, I wanted to kind of briefly discuss a second architectural anomaly. And this is something that we also just started working on, so this will be kind of like a brief teaser of some future work to come. But just to sort of provide some context for this transition, though, we were just talking about these systems that have multiple transiting planets on these kind of very nearly coplanar, nearly circular orbits. But these systems of multiple transiting planets are just kind of a subset of the full population of close-in planets. And not all of these close-in planetary systems are as sort of well aligned and they don't all have sort of nice low mutual inclinations. So the orbits can be misaligned with respect to one another and with respect to the host star. And so the anomaly I'm going to talk about is seen actually in the observed orientations of planetary orbits with respect to their host stars. So this angle between the stellar spin vector and the planetary orbital angular momentum vector is called the stellar obliquity. So in our own solar system, the solar obliquity is pretty small. It's only about 7 degrees measured relative to the mean plane of the planetary orbits. And in fact, kind of like the null hypothesis would be that planetary systems should have small stellar obliquities. Everything kind of inherits the same angular momentum direction from the disk. But observations of stellar obliquities in exoplanets show a really complicated story with many planetary systems exhibiting very large misalignments. Sometimes even the star is retrograde. So the observations, though, it's important to kind of be clear about what we can actually measure. So if we look at this kind of 3D projection of a system, this direction is our sort of direction of our line of sight. This is the direction of the stellar spin vector, and this is the direction of the orbital angular momentum vector. So in the system, the true stellar obliquity is this angle psi between the orbital angular momentum vector and the stellar spin vector. The projection of this true obliquity onto the plane of the sky is this angle lambda. And so in general, there are different observational techniques that can be used to either measure lambda, this sky projected stellar obliquity, or to measure these inclinations, these inclination angles here. In general, it's not really possible to directly measure this true obliquity psi. So in order to get constraints on that, observers have to combine multiple different measurements. And so just kind of recently did it become possible to gather a statistical sample large enough to study these true obliquities to understand patterns across the population. And so a recent study led by Simon Elbrecht and collaborators obtained a sample for which they could combine measurements of these sky-projected stellar obliquities along with these kind of line-of-sight inclinations to the stellar spin axis. So on the left here is the distribution of the sky-projected obliquities lambda for their sample, plotted as a function of the effective temperature. We can see that for these planets, this sky-projected obliquity kind of spans the full range from 0 to 180. And it's this kind of observational data that observers or that theorists have been using over the last 10 to 15 years to try to understand patterns in this population. But however, unlike this distribution for lambda, the distribution for the true obliquity psi doesn't span the full range. In fact, it appears to be bimodal, with a population of planets in which the orbits appear to be aligned with the star or nearly so, and then a population of planets that appear to be close to being sort of polar, so with the star being like this and the planetary orbit being like this. And so this sample size is still pretty small. So if this observation kind of continues to hold up as this sample size continues to grow, I think that this is kind of a game changer for the study of the formation of these systems, because before, our theories were trying to explain this, like why we could get any obliquity from 0 to 180, but now we need to explain why there would be a preference for these nearly polar orbits. Yeah?
Is there like a cosine or sine area effect? Like there's vanishingly small probability of having exactly 0 inclination or exactly 180, right? Isn't there, how does that like projection work?
That's a good question.
Like is there like an area effect sort of? How I should look at this?
Depends on what is observed, I guess. So how do you measure psi?
So psi comes from, you have to combine, so if I go back to this, they measure this angle lambda using what's called the Rossum-McLaughlin effect.
Right.
So this is where you observe planetary transits using radial velocities, and one half of the star is slightly blue shifted, the other is red shifted. So you can see the planet blocking that shifted starlight, and you can get constraints on like whether its orbit is like this or like this relative to the star. So that gives you this angle. To measure these angles, it's usually a combination of constraints from V sin I, so using spectroscopic measurements to get constraints on the V sin I of the star. And then you also have to get V, which they can do using a combination of rotational period measurements of the star, along with like the radius of the star. That together gives you V.
Yeah,
No,
but I think there's like, if the vectoral direction is random, not like if it was, like, if you were just going around a circle, that would be flat, and if you're going anywhere in the sphere, then it's different. But I don't know if going anywhere in the sphere is allowed or not. Like,
yeah, it's a good question. I don't know. I think you're right that it might be like a sin I sort of dependence.
because I think there's
Yeah, I
no
mean, you
preference
can
relative
rotate
to
as
the
needed,
observatory.
right?
Yeah,
And there's a lot more
exactly.
area on the unit
Yeah.
sphere. So
Yeah,
Whereas
Yeah.
if you're aligned, there's only 2 points on the unit sphere that
right,
give you 0. So.
right. I don't know if it would combine to sort of bias towards this way though. I don't know that you would be able to just completely evacuate the region above and below this kind
No,
of
I
thing.
don't think
probably
so.
not.
Yeah.
No,
But yeah, I think I agree.
That's really, I haven't seen that plot before. That's,
Yeah.
it's kind of amazing.
Do we know if all of the stars are single stars, or are there any multi-star systems?
So some of these would have binary companions. I'm not sure how big of the sample, but in general they would all be fairly wide binaries because the planets wouldn't be stable if it was a very close binary. So
Well, with second binary disks, you can quite easily get this polar alignment.
yeah, and I think that's like, so there have been so many different theories to explain how you can get non-zero stellar obliquities, and I think binaries torquing the disk is one idea in general. Like where you have a distant binary that can make the disk of a primary star kind of precess, and then the disk can kind of come to a separate direction from the direction of the host star. So that's one possibility. Yeah, but yeah.
I was wondering, is this the plot? Is this what you're seeing with just like a single star, or is it like, not single star, single planet, or is it like in the multi-planet systems, like all the planets are at about this angle?
Yeah. So most of these are constraints on. Well, the majority of planets in the sample are generally hot Jupiters, which don't typically have nearby companions. Yeah. So I did kind of a flip from talking about these compact multis to talking about just short period planets in general. So there are some systems though where there's like a few where it's a compact multi that has a non-zero stellar obliquity. Like there's one in particular that I'm thinking of that the stellar obliquity is like 50 or 60 degrees, and it's for both of the planets, which is kind of interesting. But yeah, most of these are, I think we usually just know of one planet in the system. But yeah, so I think that if this observation continues to hold up with more data, this is a kind of a game changer, because we need to explain how we can get these polar orbits. We're working on trying to understand the kind of dynamical origin of these polar planets, considering both their kind of orbital and physical characteristics in kind of a holistic way. So I just started working with Emma Loudon, who's a grad student at Yale, through what's called like the Ivy Plus Exchange Scholar Program. But we're studying whether the observed properties of these polar planets could be consistent with a formation channel from like a dynamical interaction via an inclination resonance. So in particular, if we consider an early epoch of the system's formation, where we have an inner planet, this is the kind of planet that's going to be that is going to turn into a polar planet. We have an outer Jupiter at around a few AU, and then we also have a sort of a protoplanetary disk that extends from around 5 or so AU outwards. So this is motivated by observations of transition disks that have inner regions sort of devoid of gas and dust. And so the interactions between the planets and with the disk causes the orbits of the planets to precess. So if you look at these orbital angular momentum vectors, they are precessing around the total. And while the disk is still there, the outer planet's precession rate is faster due to kind of the proximity of the disk. But after the disk goes away, the inner planet's precession rate is faster. So this means that as the disk kind of loses mass and goes away, it induces kind of a point of commensurability where the precession rates of the two planets are equal. And this point is a sort of resonance crossing that can cause the inclination of the inner planet to tilt all the way to 90 degrees. If certain conditions kind of line up, specifically the resonance has to go slowly enough to do that.
So this is not quasi?
Not quasi, no. Yeah.
So quasi cannot do it?
Quasi does actually predict a bimodal sort of distribution of stellar obliquities, but they're slightly offset from what we observed. So I can talk more about that, but yeah,
So why do you prefer this over? Because it's not, you say this is better.
So there's a couple things that I haven't mentioned, that some of these inner planets are Neptunes that appear to have some non-negligible eccentricities, and this this can also produce, this mechanism can also induce some eccentricities in them. Kozai can do that too. I'm not necessarily this way is necessarily, like both might be happening, but given the sort of ubiquity of inner planets with outer companions and transition disks, we think we are just kind of supposing that this might be a common thing that can happen.
So after the disk disperses, what causes the precession of the inner planet? Is it the quadrupole of the star?
Yeah, the combination of the quadrupole of the star and then the interactions with the outer planet.
Okay.
But yeah, the inner planet is faster after the disk disperses due to the stellar quadrupole.
Stellar, okay.
Yeah. But yeah, we just started to kind of explore this idea with a particular focus on whether planets that encounter this resonance at the early stage, so kind of like right at the disk hosting epoch, whether they can maintain these through to the billions of years old systems that we see today. Because maybe we can do this at the early stage, but they need to maintain those in order so that we can see them the way they are today. Yeah?
Position disk as perfectly circular, or do you consider it being eccentric as well?
We're using a disk potential that corresponds to a circular disk. It shouldn't matter too much because the role of the disk is mainly just to induce this crossing of precession rates. So as long as the disk is there and it dissipates slowly enough, it doesn't sort of matter too much about the details of the disk properties. But I just have actually one more slide to sort of sum up, and then I can go back and talk about questions on this. But I just wanted to sort of sum up by saying that these short period planets have a lot of interesting structure in their orbits, a lot of regularity, but they also have these surprising anomalies. And so today I discussed two specific anomalies. First, we kind of discussed how the outer edges of these compact multi-planet systems don't appear that they can be sculpted by just geometric and detection biases alone, which is pointing towards something interesting happening in their outer architectures, and that we can link towards dynamical and physical mechanisms. Then we also talked about how these short period planets appear to have this tendency towards either aligned or nearly polar orbits, and we're kind of looking into theories for the dynamical origins of these. But going forwards, this short period planet population continues to grow with tests just down the river at MIT. So we're continuing to kind of find unusual features in these systems and trying to explain them and understand better about how these planets kind of form, evolve, and have such a beautiful kind of diverse architectures that they do. But yeah, I'll stop there, and then yeah, happy to take further questions.
Thank the speaker for the great talk, and we have a good amount of time to take questions. Want to start with Stanford? Okay, Abby.
So these polar systems, the second planet that you have in mind that creates this configuration, it doesn't induce any radial velocity, so you can't measure it through radial velocity, the existence of that planet, because it's completely orthogonal to the line of sight, right? And it doesn't transit. So how can we figure out if it's there?
So in general, if these are sort of Jovian analogs, we would see these with radial velocities.
But it's perpendicular to the line. So where is the line of sight? Isn't it the line of
sight? So you could think of it like if we just sort of rotated this.
Are we seeing it through transits, the polar orbit?
It could be like it's drawn right there. Like it could.
Yeah, it could be like it's drawn right here.
Sorry?
It could cross in front of the star, like, and transit.
And you said in the garbage.
Like in the picture, and you would have a radial.
Yeah, but I'm talking about the other planet. It moves it sideways relative to the line of sight, always. Because
it'd be going like this. And according to this kind of, if it was drawn like this, it'd be going like this.
Right, that's the other planet.
Yeah.
Okay, but I'm saying we are looking in the plane of the transit, which is perpendicular to that direction.
So
Oh.
if we observe it like this, then
Oh, I see. So it
Yeah,
comes
it would-
behind it every now and then, you say?
yeah, we would see it like
I see.
approaching us here, receding here. So
Okay.
so like this theory is motivated by systems for which we see polar orbits for inner planets, and we also have detections of outer
So we
planets.
know about this.
Yeah, we know, like, the postulation to include an outer planet wasn't necessarily arbitrary, but there are systems for which so HAT-P11 is one example, or WASP-107, they show sort of, either we have confirmed an outer planet, or we see long-term trends in the rate of velocity suggestive of an outer planet that we haven't fully resolved the orbit yet.
Yeah, so I confess that I had previously thought that the outer limits of the Kepler systems were just the product of that they didn't transit or they weren't all that detectable. So that was very interesting that you demonstrated that it actually is real. And so I just want to know a bit more detail about how did you pick how did you assign the inclination for that test hypothetical planet, which you then excluded?
Yeah.
Yeah. So
Yeah.
Just tell me a little bit I'd love to hear how you chose that inclination.
Yeah. So we got constraints on the inclinations of the full system using transit chord ratios through transit duration. So essentially, the transit duration depends on the impact parameter. But if you take ratios of transit durations with respect to different planets in the system, you can kind of marginalize out some of the degeneracy with the stellar density. And so you can actually, it's kind of amazing, you can tell how coplanar a given system is by looking at these transit duration ratios.
So then what did you...
So then,
Yeah.
So
I got you so far, that's great.
Yeah, so we measured essentially you can think of it as like the standard deviation of the inclinations of the known system. And then we argued, well, if that planet was drawn from that same sort of a distribution of inclinations commensurate with that dispersion.
Yeah.
So, but we explored, we found we were like, well, we might be off in our dispersion measurements. And so we explored the sensitivity to that by saying, what if we are under-predicting the dispersion of inclinations? And we found that it would have to be we'd have to be a factor of 7 off to be so off that we are not finding evidence for the truncation anymore.
Yeah, I gotcha. And then for each star, did you do multiple injections?
Yeah.
Choosing, okay.
Yeah.
Great.
Yeah.
I just had a question about the migration model to explain
Yeah.
that. So if I remember correctly, you were saying that sort of the bigger planets is sort of make it through the trap, and they're the ones that become the pea in the pod planets, and then the smaller planets get sort of stuck outside. I mean, why? So is the idea then that outside of this, like a bit further out, you're forming a population both of smaller? Because I mean, these pea in the pod planets don't look that big. I mean, many of them are pretty small. Right?
Yeah.
So, like, what does larger and smaller mean here? Like, could is a smaller than the super Earth, or?
Yeah, I mean, so of course, the details of these simulations would depend on all sorts of different factors, and I'm not an expert in them. But so these regions where you get the torque reversal is something that sort of shows up in a variety of people's simulations, so it's not kind of unique to these. But I guess if we just take this plot as somewhat representative, then the larger planets are in the sort of 10 Earth mass regime, and the smaller ones are sub-Earth or so. So and you're totally right that how these continue to evolve would depend on different properties, and that maybe these smaller planets then collide and grow bigger as well. But I think if you want to form things massive enough early enough, then they kind of get sort of brought to the inner edge.
So would you explain the smaller peanut pod systems just by some other disk properties that would move the trap around, basically at the like?
Yeah.
So if you go to the previous slide where you're showing sort of the trap as a
Yeah.
function of planet mass, that depends on the details of the disk. So you could push that one out or take it out.
Yeah.
But the main point is there's the same kind of planet. That's what makes it through. I mean, is that
Yeah, I think that's the idea. Yeah, and so Watsky et al. So her paper, she did different sort of simulations of this disk migration with different sort of surface densities. That's mainly like the parameter that dictates what happens, like how much solids you have. And so they found that they were kind of able to sort of reproduce the diversity of architectures by considering a diversity of solid densities. So yeah, the idea I think is that the compact multis would represent systems for which the solid surface densities were a little bit higher. But yeah, I'm not an expert in this, but this paper just happened to come out like right around the same time as we were doing this, and I was like, oh wow, that would be very consistent. But I think it's something worth looking into further.
So it looks again in this, which is just one outcome of the model, like there should potentially be a population of smaller planets that are just outside of the detection. Right now.
Yeah.
Because I mean, they're not sitting that far out. They're like, at least in that case, a little bit beyond 1 AU, and they're not that small.
Yeah.
So is that
Yeah.
something that, are there any examples of any system where you do have sort of outlier
Yeah, I mean,
these peanut pods?
yeah, it's kind of interesting to look at just sort of the diversity of architectures that show up in these. Like, we do see some systems for which we do have smaller planets that, but these would be harder to detect. So, I don't know. I think, yeah, I fully acknowledge that we're probing on like the edge of detectability here, but we tried to account for everything that we could, and that's kind of what we found. So.
Thanks.
So in the beginning of your talk, you mentioned another anomaly. These guys who are closer into the star.
Yeah.
And one guy who got separated from
Yeah.
the piece.
Mm-hmm.
So what are the kind of explanations for that?
Yeah. So actually, I'm going to talk about these during
In
my
the lunch?
my lunch talk.
Okay,
Yeah.
then
But okay. But
we
the
will
short
wait for
answer.
half an hour, yeah. that's
The
all.
short answer is probably tidal interactions.
Right, okay.
Yeah.
Okay, so this maybe doesn't have a single answer, but from what you're learning here, is there like some way that you can look at the distribution of planets in a given system and make some sort of quantification of how dynamical its history is? So for example, these ones with like a polar orbit and a crazy neutral inclination probably had this very dynamically sculpted history.
Right.
Or things in a resonance are like at least somehow sculpted.
Right.
So is there a way to like measure that when you look at a system of planets and be like, this was a system that had a very dynamical history?
Yeah, that's a great question. I think there are so many different things you could potentially do. The main thing that comes to mind is eccentricities and inclinations. So
I see.
generally, like some kind of dynamical upheaval tends to create eccentricities.
I see.
But the trouble is that with these close-in planets that are close enough that eccentricities can be circularized. So you
Yes,
can
yeah.
partially erase that history.
Totally.
There are, so people have looked at the eccentricities of these compact multis, and in particular I'm bringing up this paper from Sam Yee in the last year or two, where they found that the eccentricities are lower than you would expect if they were purely just sculpted by dynamical upheaval. So that a period of sort of collisions and growth by impacts would have left larger remnant eccentricities than they have. These are even more circular than that. which sort of suggests that maybe the formation was pretty calm for them.
Yeah, or like they moved together, like you were suggesting.
Yeah, but yeah, I think it's mainly the systems that show like very strongly misaligned orbits, like these
Okay.
polar things, or like if the eccentricity is like 0.3, 0.4, that we kind of know, okay, something clearly happened here.
Okay, interesting.
Yeah. Yeah.
All of the computations in the system you showed were defined by calculus. Is it possible to take for our observations, take a real velocity for observation for this system to track the outer region?
So the trouble with Kepler, the Kepler sample is that the stars were pretty dim. So it's really hard to do radial velocities on them. That's where TESS has more of a power because the stars are overall brighter, but TESS doesn't observe it for as long as Kepler did. So Kepler stared at the same star field for 4 years, and that's how we were able to get out to these like longer periods. But yeah, so I think getting radial velocities for them is tricky just because they are so dim.
So how to test the model you showed in the future?
So one thing is, this may be a long shot, but so ESA is going to have a mission called Plato that will be kind of like a similar to Kepler, and will hopefully, although it's not sort of well known yet, will sort of stare at the Kepler field again. And if they choose to do that for a long enough period of time, we might be able to get, by combining Kepler with that, we might be able to get some constraints on these outer regions. It's very tricky though. And I think that, yeah, we'll probably have to wait a while before we're able to observe that region in more detail.
And Gaia astrometry would be
I guess Gaia could tell us whether there are larger planets out here that, like maybe, so I think one possibility is that maybe these things are kind of like the solar system. You have small rocky planets close in, then it transitions to maybe more giant planets out here. And so maybe Gaia would be able to help us see that. That's a good idea.
What would it look like if they did have an asteroid belt? Should I say, like, what if there was an asteroid belt outside of these, where instead of another planet?
I
Is
don't.
that completely undetectable?
Yeah, not as far as I know.
Okay.
It's too little mass.
Yeah, I think people have talked about it with like, I mean, we can detect debris disks, but they're usually like pretty scaled up, like
Yeah,
Kuiper belt
exactly.
analogs.
Yeah.
And,
Okay.
it's hard to get things that small.
I think it's time is up. So let's thank the speaker again for a great talk.